Hello and welcome back to the channel. Today we'll continue our lectures on waves. This is lecture number 4 and today we will talk about interference. Now before you go with this particular lesson, make sure you have gone to the basics of waves and at least gone over what is phase and phase difference, because that will be important to understand this particular lesson. So let's get started. Interference is the phenomena when two or more waves they interact with each other and it creates a resultant wave, and the form of the resultant wave will depend on several factors. To keep things simple, we will study interference of coherent waves. We'll talk about what are coherent waves during this lesson. But I'm getting ahead of myself, so let's start with the basics first. Let's say we have two waves. This is wave 1 and we have another wave which is traveling towards the first wave. This is wave 2. Okay, so maybe we can also say this is source 1 and this is source 2. Okay, now this wave y1 and this wave y2, when they collide at a point, obviously the particle here will be impacted by both y1 and y2. That interaction that happens at that particle, we can get the displacement of that particle by principle of superposition. What is the principle of superposition? It says the resultant displacement at the point where two waves are interacting is given by the vector sum of individual displacements of the source waves. Remember, this is a vector sum. Okay, one key aspect of principle of superposition is we add those waves, or we add the displacement of those waves at point P to get the net displacement of the point P due to those individual waves, as if y1 exists alone by itself and y2 exists alone by itself. Okay, we can also say assuming each wave is traveling alone. So interference is the event of meeting of waves, and principle of superposition governs what happens after the waves meet. Okay, so if we focus just on one point and see what happens at that point, and then if we can generalize of the meeting of waves at any other point. So this looks like it's midway, but let's say we also want to find out what happens at a different point Q. So the wave is, let's say the source 1 is spreading out waves all direction. So in that case, source 1 will send a wave in this direction. Source 2 will send a wave in this direction, and they will meet at Q. So first problem we'll solve is what is happening at one point, and then we will see how the distance traveled by each sources that impacts the resultant displacement at different points. And that together, when we combine all of that together, we'll get an idea what is happening when two waves they meet at any point in the medium. Okay, so with that said, let's just focus on P. Let us now assume both y1 and y2 are harmonic waves. Okay, y1's wave equation is given as a1 sine omega t minus kx. Let's just assume that. And y2's equation is given by a2 sine, we can take omega t minus kx or plus kx, does not matter, omega t plus kx. Both are harmonic waves. Now see, I have generalized few things. One, I have assumed that both these waves have the same omega, which means they have the same time period. And I've also assumed both these waves have the same wave number, which means they have the same wavelength. Okay? Or we can also say this is 2 pi f, which is frequency. Two waves, when they have the same frequency, they are called coherent waves. Now, if these two waves are traveling in the same medium, the speed of a wave depends on the medium. So, speed of those two waves must be same. So, therefore, lambda will also be same, because speed of a wave is given by lambda by t. So, if frequency of those two waves are same, speed of those two waves are same, then it means that lambda, which is the wavelength, is also same for those two waves. Now, there is a reason why we took coherent waves, because this phenomena of interference we can study for coherent waves. We get some patterns for coherent waves. If they were non-coherent waves, then the resultant wave will not have some pattern. So that's the reason we will study coherent waves today. Again, what are these? These are wave equations. All right. Now, just so I can show a diagram a little differently, let me draw this. Let's say here is source 1 and here is source 2. Both are coherent sources. Source 1 and source 2 both are coherent sources, which means the frequency of the wave coming out of S1 and S2 both are same. Okay. Now purposefully I will take a point which is maybe closer to source 1 and little bit away from source 2. So when this wave reaches that point, and this wave, it could have a different amplitude, but it has the same frequency and wavelength. When this wave reaches a point, what happens? You can see that S1 traveled some x1 distance, whereas S2 traveled a longer distance, which is x2. Okay, and this is our point P, where we are adding those two waves using the principle of superposition. So now, if I substitute the value x1 in this wave equation and substitute the value x2 in this wave equation, we get the individual displacements due to wave 1 and wave 2 at point P. Now, using principle of superposition, the total displacement at point P will be displacement at point P due to wave 1 and displacement at point P due to wave 2. Okay, so we can now write A1 sine omega t plus kx1 plus A2 sine omega t plus kx2. Okay. This is no more a wave equation. This is simple harmonic motion of point P due to wave 1. This is simple harmonic motion of point P due to wave 2. The total is the displacement net displacement at point P due to two simple harmonic motions. You remember when you fix x, this is no more a wave equation. This becomes simple harmonic motion of a point. Okay? Fortunately, my mic got disconnected and no sound was recorded. So I will have to improvise and do some voiceover. So bear with me. So here we see we get the net displacement of point P as a sum of two independent simple harmonic motions given by a1 sine omega t plus kx1 for y1 wave and a2 sine omega t plus kx2 for y2 wave. We can evaluate it using a method to combine two simple harmonic motions, and to do that I will rewrite this on the side like this. Y equals a1 sine omega t plus kx1, and for the second expression we'll write a2 sine omega t plus kx1, and then we will find what is the phase difference. So that will be kx2 minus kx1. So omega t plus kx1 is phase of y1 and omega t plus kx2 is the phase of y2, and I am writing the expression so that I can show a phase difference with respect to the wave y1. So rewriting the same, I can write a2 sine omega t plus kx1 plus the remainder I can write it as a phase difference delta phi. So delta phi is then k x2 minus x1. So now let's look at the second expression. This is of the form sine a plus b. So we can consider omega t plus kx1 as a and delta phi as b. So expanding it, a2 sine a cos b plus a2 cos a sine b. So now we can take sine omega t plus kx1 common. So sine omega t plus kx1, let's take that common. So what is remaining from the first one is a1, and what's remaining from the second expression is a2 cos delta phi. And remaining we have a2, we can rearrange sine delta phi cos omega t plus kx1. Okay. Now if I assume a1 plus a2 cos delta phi as a cos epsilon and this expression as a sine epsilon, then we can rewrite this as a sine a cos b plus a cos a sine b. So we can write that as a sine a, which is omega t plus kx1, plus b, which is epsilon. So we reduce this entire thing and we can indeed represent this as a sine curve, a sine omega t plus kx1 plus epsilon. So epsilon is the phase difference from the first wave. If I have to calculate the value of a, then let's square a cos epsilon and a sine epsilon and add those. So that becomes a square cos square epsilon plus sine square epsilon, which is 1. So that will equate to a1 square plus 2a1a2 cos delta phi plus a2 square cos squared delta phi plus a2 square sin squared delta phi. Now we can further simplify this as a square is a1 square plus a2 square plus 2a1 a2 cos delta phi. So the net amplitude square is given as a1 square plus a2 square plus 2a1 a2 cos delta phi. And epsilon we can get if I divide a sin epsilon by a cos epsilon, so a gets cancelled out, that's tan epsilon, so let's write tan inverse a2 sin delta phi divided by a1 plus a2 cos delta phi. Okay, so the resultant disturbance or resultant displacement, we can express that as a sin omega t plus kx plus epsilon, where the net amplitude is given by an expression which is dependent on the amplitude of the two waves, and it's also dependent on the phase difference between the two waves. And the phase difference is k times x2 minus x1. And what is x2 minus x1? It is the path difference. So we can rewrite this as 2 pi by lambda x2 minus x1. And x2 minus x1 we can think of it as the path difference of the two waves, which we can rewrite this as 2 pi by lambda delta x. So delta phi, the phase difference, is dependent only on the path difference. You can see that there is no time component here, so which means the phase difference is only dependent on the path difference and not on time. So amplitude, net amplitude, is dependent only on where those points lie, because for different points we'll have different path differences. So which in turn means for one given point we will have a fixed amplitude, and this applies only for coherent waves. So these are the important results that we get. I'll just highlight those for you. Okay, so we got this result that y, which is the net displacement at any point p, is a sin omega t plus kx1 plus epsilon. Okay, where the incident waves that were interfering was a1 sin k or sin omega t plus kx, and y2 was a2 sin omega t plus kx. Okay. Now if I generalize this point P, I can drop this x1 and we can say that this is the net resultant wave at any point x from either of these sources. Okay, where we define a and epsilon as a is given by a1 square, so which is incident wave 1's amplitude square, plus a2 square, plus which is an incident wave 2's amplitude square, plus 2a1 a2 cos delta phi. Now this delta phi is important. What is this delta phi? This is the phase difference between the incident waves. So which is k. Now because we have taken a coherent waves with same omega and they are traveling in the same medium, so they have same velocity. Therefore their wavelengths are same, so their k is same, wave number is same. We can write delta x. This is the path difference of the two waves, and this is the phase difference of the two waves. Now see, the phase difference is only dependent on the path difference. It is not dependent on time. It is not dependent on time because we have taken the special case of coherent waves. If it were not coherent waves, then omegas would be different, omega 1 and omega 2. Then we may not be able to arrive at a simple harmonic motion like this for any point P. And the phase difference would also be dependent on both path difference and time difference. Because phase difference is not dependent on time, it is only dependent on path difference. For any point P or R or Q or any other point, at all times the path difference will be same. So it will be a constant value of A at discrete points in the medium. So at any time, at whatever time you look at, those amplitudes of the resultant wave after these two waves interfere will be the same. That is the beauty of taking coherent waves. Okay? So obviously there is another thing that I should write down, which is how we define this epsilon. So tan epsilon will be A2 sine delta phi by A1 plus A2 cos delta phi. It is easier to remember this result if you think of these two amplitudes as two vectors. This is A1, this is A2. Angle between those two vectors is delta phi. And if you do the parallelogram law of addition, then this is the resultant amplitude, and the resultant amplitude makes an angle with A1. This angle is epsilon. Okay, so A value will be A1 square plus A2 square plus 2A1 A2 cos delta phi. That's the parallelogram law of vector addition, and the angle that the resultant makes with A1 is given by this. Okay, so that's a way to remember it. Now just to get a feel of this amplitude, what it is, let's table out something. This is the net amplitude. Okay, in case of string waves, more the amplitude, more the displacement of different parts of the string. So we can just say this. Okay. In case of sound waves, amplitude relates to loudness. So more the amplitude, more the loudness. So what does that mean? Let's say two coherent sources of speakers, okay, they are sending out two coherent sound waves, and I am standing at point P. At point P, I will have a constant amplitude which is given by this. Delta phi is given by the path difference of the two waves. Here, maybe it is constructive interference, which means where cos delta phi is 1. In that case, amplitude is maximum here. Okay. Now, if I move myself away from P to another point where cos delta phi is minus 1, and let's, for the sake of example, assume A1 and A2 are equal, then this will evaluate to be 0. So if I just move from P to someplace else where the phase difference is such so that the amplitude is 0, loudness is 0 at all times, because phase difference is not dependent on time. So just by me moving to another point, always the loudness will be 0. Maybe again if I move to another point, again it will be very loud. Okay, so every point there will be a definite net amplitude and by virtue of that a definite loudness. Very interesting. Now same thing in case of light waves. Amplitude of the resultant wave determines the brightness. And that's what happens in Young's double slit experiment. We'll talk about Young's double slit experiment more when we discuss light waves. You will see fringes appear. So at points where the net amplitude is maximum, it will be very bright, and then there will be another point where it will be all dark. Again, it will be very bright, all dark, like that. So that gives an impression of fringes. Okay. Now that phenomena you will only see for coherent waves, and we explain why that is. Another definition of coherent sources or coherent waves is coherent sources are such sources which maintain a constant phase difference at a given point with time. So at a given point, phase difference is constant at any time. Okay? So which means the frequency has to be same, which means the wavelength has to be same. All right. Okay. Lastly, let's talk about constructive interference and destructive interference. So we are still talking about coherent sources. Okay, so constructive interference is when A is maximum, the net amplitude of the wave is, of the resultant wave is maximum, and destructive is when A is minimum. So when will A be maximum? When cos delta phi is equals to 1. And when it will be minimum? When cos delta phi is equals to minus 1. What will be the net amplitude when cos delta phi is 1? It will be A1 plus A2 whole square. What will be the amplitude when cos delta phi is minus 1? It will be A1 minus A2 whole square. Okay. If the incident waves happen to have same amplitude, then this will be 4 times the incident wave's amplitude, and this will be 0. Okay. So here delta phi will happen at when 0, 2 pi, 4 pi, 6 pi and such, which we can write as 2n pi. And here destructive interference will happen when phase difference is pi, 3 pi, 5 pi, 7 pi and such, which we can write as 2n plus 1 pi. Okay. Similarly, path difference we can find out. Phase difference is 2 pi by lambda times path difference. Path difference will be what? 0, lambda, 2 lambda, 3 lambda and such. Here for destructive interference, path difference should be lambda by 2, 3 lambda by 2, 5 lambda by 2 and such. Okay. Okay. So that is the basics of how interference works. With that, we'll close this chapter for today, and I will see you in the next one.